So today we're going to take this idea of saying, hey, we can take these Riemann sums, these are great approximations, and go to the limit. In other words, let the number of rectangles head off to infinity so that we actually are finding area. No longer estimating. No. Now we know for sure. And we're going to do it by this method of actual limits involving Riemann sums. And it's going to be like, wow, this can get tricky pretty quick. And it might make you nervous and say, uh-oh, is everything going to be like this going forward? And the answer is no, we're going to get better tools. But to appreciate them, we have to go through and do this practice to see, oh, so this is sort of what we can do, and then get an idea of what other things we can do, which might be even better. So these are some really good, fun ideas, but they can be delicate, which means you should be practicing. So if you're following along with the video, pause and try it out yourself first. How far can you get? And then when you're ready, you can unpause, we can compare answers and see how we did. Well, this is going to be fun. Hope you're ready. Let's begin. And on a side note here, we're going to do things a little differently today. So, what are we going to do? We're going to look at some various functions. In fact, we're going to look at 5 candidates. And we're going to use some things which are known about the sums. And our goal is, look, find the area from 0 to b. And now, what do? Well, if we're thinking about it as Riemann sums, we say, okay, look, 0 to b, if we're going 0 to b, our length is b. And there's n rectangles, so b over n is our width. So that's where this is coming from. And then we're going to always take the right endpoints. So So the right endpoints have the form b over n times k. K equals 110. So we're going to look at this expression for our various terms and see what happens. So we're going to keep coming back to this as we get more information and fill it up. And at the end, we're going to return to this and say, ooh, there might be something nice going on because, ooh, there is something nice going on. It's going to be good. All right, we're going to come back. Don't forget. So, here we go. Our first one. So, find the area under the curve y equals 1 from x equals 0 to x equals b using both geometry and as Riemann sums. Well, let's think of the geometry. So here's this graph. This is y equals 1. So in other words, this height is 1. Here, this length is b. And if we look at the shape that's formed, it's a rectangle. So, okay, so the geometry says, oh, area, we can think of it as our base times height, b times 1, which is b. All right, done. But we have to do it 2 ways. Okay, so now let's switch and talk about our Riemann sum approach. So remember, what's the idea? We're going to take our limit as n goes to infinity of b over n, which was our width, the sum, k equals 1 up to n, of f of b over n times k. All right, well, what's the function f? Well, here it's 1. So we say, okay, well, this is the limit as n goes to infinity of b over n times the sum, k equals 1 to n of 1. So we have to figure out what this sum is. And there's a little note here that says recall, but even if we didn't recall that, we could probably figure it out. Because what are we doing? We're doing 1 plus 1 plus 1 plus 1 plus 1. And how many times are we doing that plus 1? N. So this sum is n. Okay, and there's a b over n times n, so the n's cancel. So we get a limit as n goes to infinity of b. And this is a wonderful limit to take Because what don't we have? We don't have any n. And so as n goes to infinity, it's always b, and therefore we get b. And you'll notice, aha, these match. Good sign. So by doing both the geometry and the Riemann sums, we got the same answer, b. Okay, well, that was not so bad. That's a warm-up. Let's come back and update this little sheet. So for the function 1, which is what we did here, our area was b. All right, great. So let's go on to our next one. So what's our next one going to be? Here we go. Find the area under the curve y equals x from 0 to b. Again, geometry and Riemann sums. Okay, so let's think of the geometry. Now, if we see this curve, y equals x, we say, oh, well, that's not so bad, because what we see here, this shaded part, that's what we're after. That's the area. And it's a triangle. We say, okay, the base is b, and the height, since this is y equals x, if x is at b, the height here would also be at b. So this is b as well. So the area, you can even see it, right? It's half of this b by b squared. So we say, okay, the geometry, area of a triangle, 1/2 base height, which is 1/2 b squared. All right, great. Done. By geometry. Well, okay, let's do Riemann sums. Okay, so if we do Riemann sums, what do we have? Well, area is going to equal the limit as we go to infinity of, now the width is b over n, because we have length b split into n equal parts. Then the sum, k equals 1 to n of f of b over n times k. So where our function f is this function, namely x. So let's see what that becomes. That's the limit as n goes to infinity of b over n, and our function, that's whatever you plug in is what comes out. It's a really nice function. So sum k equals 1 to n of b over n times k. Now, when we look at the sum, it depends on k. That's the index. So anything which doesn't involve k can be pulled out. We have to do it carefully. But in our case, notice this b over n, there's no k involved there. So yeah, pull it out. So this is our limit as n goes to infinity of b squared over n squared times the sum k equals 1 to n of k. Now, if we know what the sum from k equals 1 to n is of k, we'd be done. Well, we do. It tells us. There it is. So this is our limit as n goes to infinity of, there's still that b squared over n squared, and then this sum, by our rule here, we get a 1/2 n times n plus 1. And now, well, we can clean up, right? We can cancel off a single n, and we can write this as a limit. N goes to infinity. Well, you have a 1/2 b squared, this part here, and then you have an n going into n plus 1, which you can write that as 1 plus 1 over n, right? n into n, and into 1. And now we say, well, great, this is really easy. That goes to 1. And so we get the left over part, 1/2 b squared. And we're like, wow, beautiful. They match. Woohoo! All right, good. Now let's update. So the area when our function was x turned out to be 1/2 b squared. And at this point, you're thinking, I really like the geometry arguments. They're so short. Why do we do these Riemann sum arguments? Well, the geometry arguments are fairly limited to shapes where we have good geometrical knowledge about what's going on. And it doesn't take very long for us to run out of knowledge about geometry. So, as we're about to see. All right, so we're ready for our next one. Here we go. So, find the area under the curve y equals x squared from x equals 0 to x equals b using Riemann sums. No geometry, because that's not a nice geometrical shape. I'm not saying it's a nice shape, but it's not something composed of rectangles, triangles, and circles. Those are our basic shapes in geometry where we're great at. That's not there. So we say, okay, what do we do? Well, we go and do our Riemann sum. So our area is our limit as n goes to infinity of, we have the width, b over n, then there's this sum, k equals 1 up to n of f of b over n times k. All right, where our function is x squared. Well, all right, so we apply our function. Limit as n goes to infinity of, there's a b over n, and then there's a sum, k equals 1 to n, and here we square this, b over n times k squared. And now, let's do similar to the last thing, is, hey, the k has to stay inside the sum, because this k changes. Anything which changes has to stay inside. But the b over n never changes. It's always the same choice for b, and the n doesn't change inside the sum. It changes here in the limit, so I can't push it all the way out, but I can push it part way out. So think about squaring the b over n and putting it out to this b over n. If we do that, we're going to end up with the limit as n goes to infinity of, well, there's a b over n, and then there's a b squared over n squared. So that would be b cubed over n cubed, sum from 1 up to n of k squared. All right, good. Now we have to figure this out. Well, we actually have a nice formula. They gave it to us. So we know what the sum of the squares are. So we replace the sum. So now we're like, wow, great. So b cubed over n cubed times 1/6 times n plus 1 times 2n plus 1. And we can do a little bit right away. Notice that there's some n's. So I can take this n upstairs and cancel with 1 downstairs. So what do we have? Well, we have 2 n's downstairs, because that's an n squared. We can split it between these two pieces, the n plus 1 and the 2n plus 1. So we can write this as the limit as n goes to infinity. We have 1/6 b cubed, okay, 1/6 b cubed, then n plus 1 over n. I can make that 1 plus 1 over n. Then 2n plus 1 over n. Can write that as 2 plus 1 over n. And now we look at this and say, ooh, these are nice things. 1 plus 1 over n goes to 1. 2 plus 1 over n goes to 2. So we're going to get 1/6 times b cubed times 1 times 2. Well, that leaves us with 1/3 b cubed. And there we go. Great. Well, let's update our chart. So for the function x squared, that's one we just did, we ended up with 1/3 b cubed. All right, great. Wow. You know, it's interesting. Well, couple more entries to fill in. All right, so let's go to our next entry. So, find the area under the curve y equals e to the x from x equals 0 to x equals b using Riemann sums. So here's this curve, e to the x, the exponential curve. You can see, wow, it's going up really fast. And so we want to find the area. Okay, interesting. Now, as before, it gives us a recall. This is the geometric sum. All right, well, let's get going. And let's see where we end up, right? So our area, well, that's our limit as n goes to infinity. They have the width, b over n, times the sum, k equals 1 up to n, f of b over n times k. All right, so that's just straightforward. How do you find area by Riemann sums? That's the rule. Well, let's see. This would be what? Well, our function is e to the x. So when we plug it in, it's like we're taking e to that power. So, this is our limit as n goes to infinity of, we have b over n, then our sum, k equals 1 up to n of e to the b over n times k. Now, looking at this, we say, what can we do? Now, in some sense, we kind of have a huge hint that was handed to us, so let's exploit that. The huge hint that was handed to us is we've got to be looking for something that looks like something to the k power being added up. Well, we have the right sum, right? Sum k equals 1 to n. So we say, could we write this as something to the k power? Well, currently it's something e to something, and there's a k upstairs, but there's some other stuff as well. Now is our time to sort of flex our exponential knowledge. Oh yeah, we know about exponents. And what we can say is, we can think of it in this format, namely as e to the power b over n, and all of that to the power k. Because, remember how exponents work. When you have something to the something, you multiply the exponents together. And now, this part right here is the r. And we are like, yes, perfect, perfect. So, we can take our sum, and now, in some sense, we collapse it. It becomes a lot simpler to work with. So this is our limit as n tends to infinity. We have b over n. And now we're going to have this expression where r is this e to the b over n. So times e to the b over n to the power n plus 1 minus 1. Downstairs, we're going to have, whoops, there's a typo here. This is not minus 1. This is minus r. Sorry about that. Got to fix the typo. Okay, otherwise, we're going to be really miserable here. E to the b over n. We'll fix that in post-production. No one needs to know. Shh, don't tell anybody. All right. Downstairs, it's e to the b over n minus 1. Good, good. All right, now what can we do? Well, one thing we can do, notice in the upstairs term, both these have e to the b over n. This one actually has n plus 1 of them. This one only has 1 of them. Let's go ahead and pull that out. All right, so we're going to pull it out to the front. So if we do that, we're going to get the limit as n goes to infinity of, b over n, e to the b over n. So I'm pulling out one of these. And then we're going to be left with e to the b over n to the n minus 1. And downstairs, e to the b over n minus 1. All right. Ooh, something else happens really nice. Notice e to the power b over n to the n. You can multiply the exponents together, so this part becomes e to the b. So we're going to do one more piece of rearranging here. So limit as n goes to infinity. I'm going to write this part right here. That's e to the b minus 1. I'll put that in the front, e to the b minus 1. Then I'll put this next term here, which is e to the b over n. And this last term, it's going to be a trouble term. Because as n goes to infinity, what's happening, it's shrinking down. It's going to 0. We don't like zeros. So notice this part also is going to be trouble. Because again, b over n is going to 0. E to the 0 is 1. 1 minus 1 is 0. So I'm going to put those together and say, all right, we're going to put our troubles together. Now, several of these pieces we're pretty happy with. Let's talk about which ones we like. The e to the b minus 1, there's no n at all. So that's great. That's just going to go to e to the b minus 1. E to the b over n. Well, that's going to e to the 0. All right, we love that. That goes to 1. Life is good. We're happy. Well, that just leaves us with this thing. So if we can figure out what's that limit, we're going to be great. Okay, so time to play. What's that limit? Well, actually, that's not a game, but we can imagine. Okay, what is that limit? So let's do some work here. So we're interested in the limit as n goes to infinity of b over n divided by e to the b over n minus 1. And we can see we're going to go to b over a big number, 0. E to the 0 minus 1 is going to 0 over 0, which means, of course, more work. Yes, we got to do some more work. What is the more work? Well, le hôpital. Aha! Le hôpital, mon ami! Ah, it has been too long. So, we'll do le hôpital. Now, keep in mind, what's the variable? In other words, what's the part that's changing? It's not the b, it's the n. All right, so upstairs, taking the derivative with respect to n, what would we have? Well, if we think of it as like 1 over n, derivative of that would be minus 1 over n squared, so minus b over n squared. Downstairs, all right, do the chain rule. It would be e to the b over n times the derivative of b over n. Well, that's still minus b over n squared. And then the derivative of minus 1 is 0. And now we're like, whoa, this is good. Because we see these pieces cancel. And so we're like, wow, this is simply the limit as n goes to infinity of 1 over e to the b over n. And now this is something we're happy with. We're ecstatic to have this one because e to the b over n is also known as, well, it's also going to go to 0, right? B over n goes to 0. Hold on, let me back up. E to the b over n does what? B over n goes to 0, and e to the 0 goes to 1. So this is 1. All right, good. Whew. All right, well, so updating, that part goes to 1, and now we know what everything does. So we're going to get e to the b minus 1 times 1 times 1, and therefore our area is e to the b minus 1. That's it. Beautiful answer. Okay, well, time to update. So when our function was e to the x, that's what we just did, our area was e to the b minus 1. Good. All right. Well, interesting things going on here, but we should do something else. We should do one more, right? Because there's one more entry. And here, we're going to go. Find the area under the curve y equals the square root of 1 minus x squared from x equals 0 to x equals b using geometry. So we're not going to do any of our Riemann sums, all geometry. All right, well, let's see if we can reason what's going on here. Well, one thing that we can do is to think about the shape here, right? Because you'll notice there's a little dotted line, so you can really think about it as two parts. So there's one part, which is a little triangle, and then there's a second part, which is this part of a wedge. It's like a piece of a pie or maybe pizza or something, but we have those two pieces. So if we can understand what's happening to those two parts, then what we can do is just combine and get the answer. Now, here we say, all right, we know the x-coordinate is b, and the y-coordinate is the square root 1 minus b squared. So, how can we use that? Well, one thing we can use that to do is to say, okay, so it must be the case that this area, this triangle, we know the base and the height. So the area of the first piece is 1/2 times the base times the height. 1/2 times b times square root of 1 minus b squared. Okay, all right, that's not so bad. Kind of interesting. How about the second part? Okay, well, for the second part, we're going to have to think about what's going on. It's a wedge, part of a circle. So in general, we can just quickly remind ourselves, if we have an angle here, and circle radius r, then what we can say is that if we look at the area of the wedge that we're after versus the total circle, we can in some sense think of this, what's the proportion of the wedge? Well, that's the same as the proportion of the angle to a full revolution. So that's just theta over 2 pi. And so, multiplying, we get that the area is 1/2 times the angle times r squared. Now, in our case, we're circle radius 1, because this is 1. I guess we didn't actually say it explicitly. This is a circle. Okay. You can square both sides. Y squared equals 1 minus x squared plus y squared equals 1. So we say, fantastic. If we know this angle here, then we're good to go. Now we just have to sort of think about, well, where does that angle show up? Well, there's a couple ways to do it. Now, here's one thing to observe. There's this other angle here. And this angle, we'll call it alpha. It just needs a name for the time being. What's true about those two angles, theta and alpha? Well, they are complementary, which is to say, if they happen to run each other when they're out and about in their days, they would say, very complementary things. Like alpha might say, theta, that's a wonderful hat you have. It looks quite smashing on you. To which theta might say, and alpha, have you lost weight? You're looking wonderful, right? They just give each other compliments. They're complementary angles. Okay, so what does that mean? Well, really means that they add up to a right angle. Now, here's another thing. Look at this angle up here in the triangle we talked about before. This is also complementary to alpha. Now, what does that mean? It means this angle is also theta. Now, why do we mention that? Well, what we can do is now we have theta inside a right triangle. And we say, okay, and in particular, we know the three sides. B, square root of 1 minus b squared, and the hypotenuse is the radius of the circle, which is 1. Now the easy sides are b and 1. So, since that's the opposite side to theta and the hypotenuse, we can say, aha, sine of theta, opposite over hypotenuse, is b over 1. Or we can say theta is arcsine of b. So we say, great. So the area for the second part, well, that's 1/2 times theta times 1 squared. So it would be 1/2 arcsine of b. Now put the two together. So our final answer, 1/2 times b times square root 1 minus b squared plus 1/2 times the arcsine of b. And there we go. Wow, what an answer. What an amazing answer. Definitely, you think about a circle, you think, wow, it seems a little bit more complicated than you might have anticipated. But okay, so at least we know the area. Now, on a side note, we don't know how to do this by Riemann sums, but now we can kind of go backwards. And we can say, well, what would be the Riemann sum? So the Riemann sum would be the limit as n goes to infinity of what? B over n times f, remember that's the width. Whoops, not f yet, sum, sum from 1 up to n, f of b over n times k. Well, all right, we know our function. That's our function. So this would be our limit as n goes to infinity of b over n times the sum, k equals 1 up to n, of the square root of 1 minus bk over n squared. Okay, well, yes, that's what it would be. Okay, so now what? Well, now what we can do is we can say, for example, we can get a common denominator. We could write this as n over n squared on the inside. And then we could say, okay, then n squared in the denominator, you can pull it out of the square root, pull it all the way out to here, so that we could write this as the limit as n goes to infinity of b over n squared, so that b over n plus an n coming from inside the square root times the sum, k equals 1 to n, of the square root n squared minus b times k squared. So this Riemann sum is the area. So these have to be equal. And if you look at this, your sort of first reaction is, really? Wow, that's not so clear that those have to be equal at all when you stare at this. But it says, no, they really are. They truly are going to be equal as you let n go to infinity. And, okay, well, interesting. So there's kind of two things you can do with Riemann sums. It's like, well, if you know how to simplify a sum, then you can find an area by taking the limit. But the other thing is you can say, well, if I can find the area in a different method, then I can figure out what does the limit of the Riemann sum become. So, well, it goes both ways. Well, let's go back to our chart, because this is the last entry, that missing entry. So this last entry, square root of 1 minus x squared, okay, that one a little bit longer, but okay, we got space. we can write it out. So it was 1/2 b square root 1 minus b squared plus 1/2 arc sine of b. Now, let's put on our math hats. We're in a math class. We should put on our math hats at some point in time and start asking ourselves the question, do we see a nice pattern coming out here? Because if we did, that would make us say, and probably make us say, ooh, that would be nice if it was true. Well, there's kind of a pattern going on when we think of like 1x x squared, right? Because you can think of like, oh, I went to b squared, b cubed. You could almost guess what the next one would be, like b to the 4th. And then the coefficient, it's not really saying it here, but you could think of it as like a 1 over 1, right? So you would anticipate the next one should be 1/4 b to the 4th, and so on. But, you know, x squared, and then you have like 1/3 something cubed, sounds really familiar. Kind of sounds like an antiderivative, doesn't it? Let's take the derivative and see, does anything interesting happen? So when I'm talking about the derivative, I'm really talking, think of this as our variable now. So the derivative of b, where b is the thing that can vary, well, that would be 1. Okay, that kind of matches. Here, derivative of 1/2 b squared, well, okay, the 2 comes down. 2 times half is 1. I'm left with b. Oh, that kind of matches there. How about 1/3 b cubed? 3 comes down. That'd be 1, and a b squared. Oh, well, that kind of matches. E to the b minus 1. Well, the derivative of e to the b is e to the b. It's a beautiful function. Minus 1. That's 0. Ooh, that matches. Oh, are you kidding me? All right, I'll tell you, if this derivative matches, I'm just going to be like, what? Okay, let's find out. Oh, I'm kind of curious. Oh, I hope it works. Okay, because it would be nice if it's a pattern that holds, right? Okay, so let's do it carefully. Product rule. So derivative of the first, that's 1/2, and then times the second, square root of 1 minus b squared, plus the first, 1/2 b, times the derivative of the second. Well, think of this as 1 minus b squared to the 1/2 power. So the 1/2, then would be 1 minus b squared to the minus 1/2, then times minus 2b. Plus, now the derivative of arc sine. Ooh, do you remember that one? That one's an interesting one. It's 1 over the square root 1 minus x squared. Now, if you didn't remember that, there's ways to rederive it. Except it's not x, it's b. Okay. All right. Well, lots of halves floating around here. Well, what can we do? Let's see. Well, we can do a little bit here, right? Because there's a 2 and a minus 2.5. Okay, that's something. And what else do we have? Well, we have a bunch of 1 minus b squareds. So let's factor out 1 minus b squared to the lowest power. In our case, it would be 1 minus b squared to the minus 1/2 power. And let's also factor out a half, since everything has a half. So I'm going to pull out a 1/2, a 1 minus b squared to the minus 1/2. And let's see what's left. From the first term, we got the half. Here, we pulled out 1 minus b squared to the minus 1/2. There was a 1 minus b squared to the plus 1/2 to begin with, which will leave us with 1 minus b squared to the plus 1. Think of it as a half minus minus a half. Now, in the second term, we got that already pulled out. Great. We got the half pulled out. That half and 2 canceled. So we're left with the b and the minus b, which makes this a minus b squared. And then from this last term, well, we got the denominator pulled out. We got the half pulled out, so we're left with plus 1. Oh, Okay, so this part here, really, notice it's a 1 and a 1. So it's like 2 minus 2b squared, or 2 times 1 minus b squared to the 1. Now, 2 times a half is 1. 1 minus b squared times 1 minus b squared to the minus 1 half is 1 minus b squared to the plus a half. Which means, wow, that our derivative is the square root of 1 minus b squared. What? Oh my goodness, wow. So somehow, when we're looking for the area under f of x, that these pieces that were showing up have something to do with antiderivatives. There's got to be something here. There's got to be something really, really cool and beautiful going on. Oh, this is good stuff. And I'll tell you, whatever it is, it's got to be really important. I bet you people might even say it's going to be very fundamental. But that will be for another session. Thanks for coming. Hope to see you again. Bye.